So in the last video, there's something that we mentioned but also sort of neglected. What is the mass of a boron atom? Well, if you look at the periodic table, the bottom of the periodic table says 10.8. Does that mean that boron has 5.8 neutrons? Would we write it like this? No way! This is the effect of multiple isotopes that naturally exist for boron. So boron has two main isotopes, boron 10 and boron 11. There is no boron atom on the planet that actually weighs 10.8 AMU. It's the mass on the periodic table is an average of the isotopes, a weighted average. So this 0.2 and 0.8, those are the natural abundances of those two boron atoms. So 10.8 is the weighted average of boron. 10.8 is closer to 11 than it is 10, so that's how I know that the 11 isotope is greater percentage than the 10 isotope. Make sense? So we can measure and take the mass of things on a scale in the lab, on a balance in the lab, but how do you measure and take the mass of something as tiny as an atom or a molecule? In labs, we use a mass spectrometer. So this is a mass spectrometer. This is an image from your textbook. The way a mass spectrometer works is you inject a sample. It can be a liquid sample, but eventually that sample has to be vaporized and gotten into the gas phase. It's hit with a beam of electrons, and once it's hit with a beam of electrons, your sample gets turned into cations. That's because when one electron runs into your sample, it will knock off another electron or sometimes break it down into smaller pieces. If it's a molecule, we'll get there one day. Goes through a couple of accelerating plates, yeah, sure, and then through a magnet. That magnet, because your particles, your sample is now a charged thing, a positively charged cation, that magnet will sway the course. It will bend the course, the path that your molecule was headed down. And so if it bends that a lot, you know one thing. If it bends it not so much, you know a different thing. So the magnet, depending on the angle that it bends your original path, you can tell a couple of things about your molecule. If it bends it a lot, it means it was a light atom. Think about pushing this little guy around. It's very easy to push him and get him to be deflected far from his original path. But if something is not deflected very far, we're going to say that's the heavier atoms. Heavy atoms do not get deflected. Imagine trying to push this guy around. It's not so easy. So let's go back to boron. Actually, sorry, let me point out that this, if you look really closely, is a neon thing. That's neon 20, neon 22, and actually neon 21. There are three naturally occurring isotopes of neon, and the height of this peak tells you which one is most abundant, which one is present most in nature. So neon 20 is most present in nature, neon 22 is next, and then neon 21 is the least. There are percentage numbers beside here, if you can see that. It's very tiny, I know. But on the periodic table, neon's mass is closest to 20 because that's the most abundant isotope. Okay. Back to the boron. Here's a mass spectrum plot of what boron would look like. If you just took a mass spectrum of boron atoms, you would get a peak at 10 and a peak at 11. And the peak at 11 is much taller than the peak at 10 because they're in an 80-20 ratio. That's if you take a mass spectrum of atoms. What if you take the mass spectrum of a molecule? Well, if we're going to take the mass spectrum of BF3, we could have boron 10 or boron 11, along with 3 fluorines. And if I know that 100% of fluorine on the planet is F19, I can put in a 19 for each of those, and I don't have to do a bunch of gymnastics to figure out the masses here. I just add those together. Those kind of look like 8s, but those are all 19. I get a mass of 67 and 68. This one is a 20% height of that one. That's because the boron 10 and boron 11 are solely responsible for the ratio that you got there because F19 is 100% of the fluorine on the planet. Make sense? Maybe, kind of, I hope. Okay, there are some other things that have some very high percentage isotopes. What if I look at the mass spectrum of CH3Br? The mass spectrum of CH3Br looks like this. What? Where I've got two peaks that are about equal height, one at 94 and one at 96. So if I know that I've got two different isotopes of bromine, if I didn't already know that my two isotopes were 79 and 81, the way I can figure that out is 94 minus carbon 12 minus 3 times hydrogen 1. So that's 94 minus 15. Yep, that gives me 79. That's 96 minus carbon 12 minus 3 times hydrogen 1. That gives me 81. That's how I know that this is CH3Br. And the reason for the two peaks is because bromine has two separate isotopes. Because the height of these two peaks is about the same, I'm going to say about 50% of the bromine on the planet is bromine 79, and about 50% of the bromine on the planet is bromine 81. There are a couple of isotopes that are like this that have pretty large percent abundances of each type. So if I'm reporting the mass of bromine on the periodic table, if it's 50-50, I expect the mass on the periodic table to be about 80. If you look out the periodic table, yeah, it's about 80. Officially, it's 79.9 grams per mole. So, yeah, that's about 50-50. There's officially a little bit more bromine 79 on the planet. Okay, what about nitrogen? Nitrogen has two naturally existing isotopes. But if you look at the spectrum, the mass spectrum of nitrogen, remember nitrogen is a diatomic molecule, so you're not just going to get a single solo nitrogen atom, you're going to get the spectrum of diatomic nitrogen in two. What would this spectrum look like? The two naturally occurring isotopes are nitrogen 14 and nitrogen 15. So if we're looking for a spectrum of diatomic nitrogen, that means one nitrogen could be nitrogen 14 and the other nitrogen 14. That means one nitrogen could be nitrogen 14 and the other nitrogen 15. It also means you could reverse the ratio like so, reverse the roles, a 14 out of 15, a 15 out of 14, or 2 15ths. So hopefully, because you already know how this is going to work out, your biggest peak is going to be, by far, this one. Because 99.6% of the nitrogen on the planet is nitrogen 14. How do you know that your biggest peak is going to be at 28 AMU and not 29 AMU? Or 30 AMU? You take the percent abundances and multiply them together to tell you how tall that peak should be. 0.996 times 0.996, 0.996, dang it, times 0.004, because we're taking it out of the percentage, 0.004 times 0.996, 0.004 times 0.004. Do that math and report back. Got it? We got 0.992 or 99.2% for the first one, 0.398%, 0.398%, 0.0016%. What are all those percent numbers? That tells you the percent height, really, of the peak at that AMU. But notice these middle two are at the same AMU. It's two different combinations, but it's at the same AMU. So our height at 29 AMU should be 0.797%. So it's real confusing, I know. But a mass spectrum of this guy would have a peak at 28, 29, and 30. It would have a giant peak at 28, a baby blip, and a super baby blip at 29 and 30. Yeah? You're going to have to draw or calculate a couple of those in your chem activity in a moment. But before I turn you loose just yet, the chem activity that you're going to do has this kind of mass spectrometer. It's slightly different from the one I showed you in the beginning. It's called a time of flight mass spectrometer. And it's all about lighter particles move faster than big particles. Big particles are heavy, they move slow. Light particles are small, they move fast. And so it actually takes longer time for bigger particles to hit the detector. And then in all the translation, to get this spectral output, it's all about how long it took for that particle to hit the detector. It's not about the angle of deflection. Light particles hit first, heavy particles hit later. Yeah? So the time of flight, it's all about the time of the flight. I can't believe I just said that, but yeah, it's the truth. And then the original picture was about angle of deflection. But it's all about heavier masses, lighter masses, and how they react differently. Okay, that's really good enough.